right, thank you, Tracy. As she said, my name is Kevin Pitstick. I'm here to talk about foundations for summarizing and learning latent structure in video. This is a sort of a new line of work that we started this year, and it's based off of work of one of our collaborators on campus, Carnegie Mellon University Machine Learning Department, Professor Eric Shing. And he did some work on video summarization, which sort of inspired this work. To start off with, I just want to talk about the DoD operational deficiency that inspired the work. There's a lot of streaming and archive surveillance video that's being gathered across the DoD, Air Force, Army. Everybody has sort of their own capability of gathering video. And one of the things that we've seen and heard, especially from our collaborators at AFRL, is that when it comes to research, there are various groups that are looking at ways of applying computer vision and automation to process the video. The operators themselves, the PET analysts, processing, exploitation, dissemination, for example, they do not necessarily have the tools to help augment their capabilities. In talking with the Air Force, for example, they said that all of the video streams that they have are being monitored 24/7 by humans, and so that takes a little bit of a toll on, a lot of manpower, and it takes a toll on the people doing the work. The other thing I wanted to call out is one of the projects we're excited about that was recently started, Project Maven. They're actually starting to look into the same line of work of providing computer algorithms. And one of their first tasks that they're looking at is applying computer vision algorithms to assist these analysts. So to give a little bit of background on the project, there's a computer vision task known as video summarization. And probably the best way to describe it is, given a movie, can you produce a trailer that includes all of the interesting key and unique segments? And so the computer vision task is designed to, given the input of video, output a portion of the video which best summarizes it. Some of the current techniques, there's pulling out what are the keyframes of the video. There's also a task which looks at pulling out consecutive key subshots from the video. And then there's also some various lines of work that look at pulling out the key objects themselves. You're sort of doing object detection on the video. What we wanted to look at was sort of a new video summarization task where we're looking at generating video summaries by looking at the key objects that occur in the videos, and in particular, what sort of motions they are partaking in. And so the summaries that we're producing, sort of the two main questions we want to answer are, what are the representative objects that are in the video, and then what actions are these objects partaking in? Our approach is to develop a new video summarization pipeline. And the first stage is, first we need to extract the clips of the objects in motion. This step consists of some of your standard computer vision algorithms, such as object detection, multi-object tracking between frames, and then there's another step where once we have the object clips, we say, what are the representative motion segments for each of these objects, and then segment them. Next, we extract features using the last layer of the object detection algorithm, and take these features and feed them through a computer algorithm known as an autoencoder. An autoencoder is basically a neural network that, given an input, its goal is to recreate that input as its output. So the last stage of the pipeline is the clips which are given as input but cannot be constructed and cannot be constructed well as output. Those are things that the autoencoder has not seen before. These are things that the autoencoder has not learned, and therefore we put those in the summary as the key and unique segments. Once we've processed these object motion clips, then we feed them back as online training into the algorithm so that it sort of learns on the fly, and if it sees something similar again, it's likely it'll be able to reproduce it better next time. Sort of the two key contributions for the research we're doing is using object motion clips to depict the video and to generate the summaries. And then also the online motion autoencoder model itself, which is the last part of the pipeline, which has sort of been constructed uniquely to encode and learn these motion patterns. I do want to call out our collaborators, Xiaodan Liang and Eric Xing. They're very instrumental in this work. Here's sort of a visual overview of the pipeline. Again, first you need to extract frames, do object detection, track the objects through the frames. If you have a still camera, one of the things you can do is remove still objects. Motion trajectory segmentation, a good way of thinking about that is if you're tracking a car and it's moving straight and then suddenly it turns, you could separate those into sort of two different segments. The feature extraction from the clips, and then finally the online motion autoencoder portion, which yields the video summary. So getting into the experiments, one of the data sets that most of the work was done on is sort of a new data set that was put together, Orangeville. It's looking at surveillance data at intersections. In addition, there's some various other data sets, base jumping, SumMe, TV Sum. These are all standard data sets that are used in video summarization and are good to sort of get an idea of how well this works in comparison to other research work. Key metrics used in the field: area under the curve, average precision, F measure, using a threshold of 0.5. For the Orangeville data set, we looked at summarization on the object level. For some of the other data sets, we looked at sort of subshot level in comparison, since those data sets did not work at object level summarization. So here is an example of one of the results. On the left side, you'll see the original video. It's about 100 seconds. On the right side is the summary, which is 17 seconds. And it'll be blacked out when that part of the frame has not been included in the summary. And it might be hard to see. There are some red bounding boxes around the parts of the video that have sort of been picked out as the key object motion clips. The other object clips that aren't picked up were deemed by the algorithm to not be a key part of the summary. And so one of the things you'll notice with the video is that the sort of clips that we aim to pull out are fast-moving vehicles, pedestrians walking, things that if you see a car turning right, then the idea is that we hopefully don't pick it up a second time. So I will move on to the next one. This is just the summary itself, about 17 seconds, and you can see back to back all of the clips that were pulled out as interesting. So in looking at the results, one of the things about video summarization is the results can be a little bit subjective. So they had to be ground truth annotated by a panel of human subjects, and they were explicitly told to annotate fast-moving cars, people crossing the road, cars turning, cars moving very slowly or sitting still. They were told not to annotate. And then we did some comparison across some competing summarization algorithms, sparse coding, which has been used in some of Eric Xing's previous work, as well as different variations of autoencoders that appear in literature. And then there was also some qualitative analysis where subjects were asked to watch the original video at an increased speed, and then to watch the summary slowly and assign a rating between 1 and 10. For some of the other results, again, these don't work on the object level, and so these ones were, the pipeline was modified a little bit to instead of picking out the object clips, it was modified to pick out the key frames, or the key frame subshots, and it was compared against a few other baselines. So these were the SumMe and TV Sum results. To sort of switch gears for just a second, one of the things that we're interested in is applying these algorithms to DoD, FMV, full motion video. One of the challenges is that If you look at in the previous video, it was a stationary camera looking at cars. Actual DoD aerial video looks very, very different. And here's an example, publicly released CENTCOM video of sort of infrared video over a compound over in, I believe it was Mosul, Iraq. And they're sort of keen on and trying to pick out the individuals who have guns and the individuals who do not. And there are some hostages in the video. And so some of the key differences between the sort of video we were looking at and this video is you get switches between infrared video and electro-optical. So your algorithms have to be tuned to that. Obviously, a moving camera introduces some other difficulties because you may not necessarily know whether it's the camera that's moving or the objects themselves. The aerial viewpoint versus a ground viewpoint actually influences object detection quite a bit. Most of the traditional object detection models that we have are focused on larger objects that take up most of the screen, not on tiny objects. And in addition, there's also this various, rapidly changing zoom levels and panning, which can create segments which are sort of disjointed. And so in the past few months, we've been working with Daryl Lochtefeld and Daniel Zellick from AFRL's Human-Centered ISR division to get a better understanding of the sort of video they're looking at and how we might be able to apply these algorithms in the near future. To sort of wrap up the project artifacts, we do have a prototype utilizing this pipeline. In order to perform the annotations, we have a video markup tool where you can annotate the spatial temporal object clips within the video. We have a submission to IEEE, transactions on cybernetics. In addition, we do have some data set, the Orangeville data set that contains annotations as well. And we just started doing some work on detecting vehicles and IR surveillance data as sort of the front end of the pipeline. So to rapidly conclude, the big problem we're looking at was how we can help condense the volume of video that the DoD has to offer, and we wanted to look at video summarization techniques as a way to help reduce the size of the video into smaller clips. We got the results. We had some good experimental results with competing benchmarks, and we in future work we do have a FY 2018 project summarizing and searching video where we want to extend this, and hopefully we want to test on some aerial FMV data sets specifically, and we also want to extend the work to detect and search for specific actions and activities happening in video. One of the things that came up when we were speaking with our AFRL collaborators is that depending on the particular task at hand, some things may or may not be interesting depending on who's looking at the video or what the actual project is. And so being able to say, this is exactly what I'm looking for, and then search the video for it is something that's definitely important. And then we want to continue our AFRL collaboration to get a better understanding of what their needs are. Again, I'm Kevin Pitstick. The primary investigator is Ed Morris, and then we had, I want to call out especially the CMU and AFRL collaborators as well as our team. So I have a little over a minute for questions, if anyone has any questions. Microphone's coming your way.
Yeah, so one of the things that actually we interact with you on a fair amount is verification and validation.
Mm-hmm.
I don't know if you're part of that effort, but...
I'm not.
Okay. I mean, can you just say anything about how you would actually take this video and do V&V on the quality of the output, kind of as different data sets and different algorithms are applied, and where you might think to go with that, or just say there's other people who are doing that, and maybe you should talk to them.
So if I understand your question correctly, one of the things we could do is putting the video in front of an analyst, saying, is this useful to you? Another thing is I know a lot of the analysts will take part of the final report that they have to produce. They create logs of things that were interesting that they picked out, and so seeing if there's an overlap between what our summary produces and the things that they were looking for, seeing what sort of overlap there is. Is that sort of where you're going, or?
Well, it's also literally putting error bars or risk metrics on the output of the algorithm itself. I mean, you had some, whisker plots there of, confidence intervals, and the question is, I mean, one of the things we've been working on a slightly different project, but related, is putting that in a routine way on any algorithm that does this kind of analytic, where you have different data sets and different, algorithms, giving an analyst results, and they need to know whether they can trust, what's the probability it did find what it was looking for versus miss it or, find it when it wasn't there.
I see. Yeah, so I believe there is a group that I don't particularly work on, but there is another group, and we can definitely talk afterward.
I think the intent is to put you together with that group.
Okay, yeah, definitely. Let's talk after, and we can go for it. Any other questions?